have noticed that all of our cross-sectional traces so far have been either hyperbolas or ellipses. Now, occasionally we've gotten degenerate ones, degenerate ellipses in the sense of just a single point, degenerate hyperbolas in the sense of intersecting lines. And with the hyperboloid in two sheets, we sometimes got absolutely nothing. But what we haven't seen yet is a parabola. Well, the way you recognize you're going to have a parabola is that not all of your variables are squared. Because, of course, the usual parabola that we're used to thinking of is y equals x squared. One variable is squared, the other isn't. So I've got two equations up here on the board. These are actually the last two examples that we're going to take a look at. And you can see, in both cases, I'm not squaring the z, but I am squaring the x's and the y's. And I happen to have just solved for the variable that's not squared. That's often done. Doesn't have to necessarily be given that way, but you might choose to rearrange things to solve for the variable that isn't squared. I want to just point out that here, both of these would be centered, and the term center is actually slightly inappropriate for this. This is going to have a vertex rather than a center, whereas this one will actually have a center. But both of these are centered, for lack of a better word, at the origin. I haven't translated anything in any direction. So if I look in the xz plane, I'm going to have a parabola that opens up. And if I look in the yz plane, I'm going to have a parabola that opens up. So my cross-sectional curves are parabolas that open in the same direction. And that right there really sort of suggests the shape that I'm going to get. It looks like I'm going to get some sort of a bowl that looks something like so, with a parabola here, and I'm guessing elliptic cross-sections elsewhere, and then I'd have a parabola in the other one. Turns out that's going to be what we're going to get. We'll work through it to see that that actually is correct. This one's a little trickier to see, though, because notice here, in the xz plane, we'd have a parabola that opens down, and in the yz plane, we'd have a parabola that opens up. So we're going to have something more like so. Much harder to see what that shape is going to look like. This one is the toughest one to understand, the toughest one to draw. That's what we'll take a look at in the next video. But that's the key thing you want to look for when you've got parabolas as cross-sections. You will always have two of them, and it's a question of do they open up in the same direction, which is kind of nice, or do they open up in opposite directions, which tells you you're dealing with the most complicated example. All right, so let's just take a look here. We said in the xz plane, which would be y equals 0, we were going to get a parabola, because then we're just getting z equals x squared. So that's just my standard parabola like so. Similarly, in the yz plane, which is where x equals 0, I'd be getting z equals y squared. That's just a lovely parabola that opens up. Now, if I look in the xy plane, which is where z is equal to 0, I get 0 equals x squared plus y squared, and that's awfully boring. There is a solution, but it's just going to be a single point. Okay. So I'm going to want to move to a parallel plane, and here I cannot move to a negative z value, because z has to equal x squared plus y squared, which is never negative. So I could move up. Let's move to z equals 1, which would be parallel to the xy plane. Then I'd have 1 equals x squared plus y squared. Oh, that's just the unit circle. Okay. So that's an example of an ellipse, but it's a degenerate ellipse. It's a perfectly round one called a circle. Okay, so if I now want to sketch this in 3 space, I've got 2 parabolas and an ellipse, so I'm going to draw the oddball one in the middle. Okay. And I like to start in the yz plane if I can. So there's my parabola. Then I've got that circle, and then I'd have a parabolic trace in the xz plane. And now I'll go ahead and draw in my axes. Okay, so it does look like this. We call this an elliptic paraboloid. That's the general name for this. Of course, in this particular case, because my ellipses are going to be circles, I could call this one, if I wanted to, a circular paraboloid. But in general, if you've got this sort of a bowl shape, it's paraboloid, it's an elliptic paraboloid in all cases, and if the ellipses happen to be perfect circles, you can call it a circular paraboloid. All right, so in the next video, we'll take a look at the hardest example, which is what if we've got parabolas that open in opposite directions.